Okay. All right, thanks. Which one? Which one's wrong? Oh, the first part? I haven't even told you what it is yet. All right, okay. You have to wait. It will be wrong later, but it's not wrong yet. So this is a problem, and it's an interesting thing in oceanography. And this is something that's been known for a long time, like in Norway. Off the coast of Norway, up here, there's something called the Lofoten Basin. And these are the richest fishing ground in Norway. So this is where a lot of the cod comes from. And it's been known for a long time that right out in the, this is a zoom in of the basin here. Right out in the middle of this, there's a large vortex, anticyclonic vortex, which is spinning around here. And it's been there as long as the records have been. It's in the ocean. That's right. It's in the ocean. So this is this is an ocean talk. Everything's in the ocean. And it's been known, and it was first described in the Russian literature. So there were some Russian scientists who described this, and they had some ideas about it. But it's always there. So, and as long as the satellite records have been there, it's been there as well. Some question about how big it is. The satellites, according to satellites, it's 100 kilometers, but it's probably more like deformation scale, approximately. So that's in Lofoten. Off the coast of the east coast of North America, there's another one, an anticyclonic eddy, which is also well known, called the Man eddy. And this is, so the Gulf Stream comes up here, and then it diverts, a branch of it diverts in this direction and continues up. And then right offshore here, there's a feature which is trapped over a topographic basin, which is anticyclonic. And that thing tends to be there as well. So Tom Rossby put in some floats over there, and they circled around, and he was able to describe the size and approximate form of that. There's another example. This is off the UK, in the Rockall Trough. There's a feature that's out here as well. I guess it's not in this picture. That's the Rockall Trough, but the feature is there. Also anticyclonic and centered over this depression in the bottom. So these things are always circulating around like this. That up there is a seamount. The vortex would be right here. If you can see over here, that's where the vortex lies. There's a seamount up there. That's the Rockall Plateau, and it tends to be here. But this is not even really a basin. This is a trough. So, and it's still, you get that over there. Okay, so, and there's a lot of other examples too. So in the Pacific as well, and we have these things. So the common features are, this is, the vortices tend to be anticyclonic. They're large. It's a question of how large, but probably deformation scale or larger. And they're surface-intensified. So there's some evidence that some of these things go all the way to the bottom, but they definitely are strongest at the surface. Okay. Now, this is a simulation, and this is rotated. So this is Norway down here. So this is west in this direction. So you have to think tilted a bit. We should rotate this thing by 90 degrees. But anyway, this is a high resolution simulation of this region of the Lofoten Basin. And the usual thinking about this vortex is this was supplied by single anticyclones migrating off the slope here. This is the continental slope into the basin and merging and then feeding that anticyclone. But if you look at a snapshot like this, what you see is that it's not just single anticyclones. You really have vortices of both signs. So you have the red, you have cyclonic vortices, and then you also have the blue, anticyclonic vortices. And if you look carefully, you might also notice, this is something that's going to come up again and again here, is that there's an asymmetry in this basin. The cyclones tend to be elongated. They tend to get shredded into filaments, whereas the anticyclones tend to retain their axisymmetric shape. So you have much more circular looking anticyclones. So there's an asymmetry between cyclones and anticyclones in this basin. Okay. All right. Now, because of this, really what we're talking about is large-scale turbulence, so balanced flows, geostrophic flows, over topography. And this is something that goes back to the 70s, where people were studying this, beginning in the 1970s. There was some earlier papers, but there were two papers that came out that were really influential, took two entirely different approaches. This is Rick Salmon, Greg Holloway, and Merle Hendershot took a statistical mechanical approach to the problem. And then there's another one by Francis Bretherton and Dale Hayvogel, which uses a minimum enstrophy argument. And there was a subsequent paper in 1987, so it came about 10 years later, which showed that these two approaches give basically the same result. So as long as the resolution in your model is infinitesimally small, these two approaches give the same approach. And this one is actually quite easy to understand. So that's what we're going to focus on. Now, two-dimensional turbulence, one of the main things about two-dimensional turbulence is that energy tends to cascade to larger scales. So if you look at the stream function, which is like the pressure, what you tend to see is that you have large-scale structures that merge. So these are anticyclones merging and cyclones merging, and they make more and more. So we've heard some discussion about this event. You wait long enough, and eventually you just have a dipole. But if you look at the vorticity, instead, the vorticity tends to be strained out in between the vortices. So you have a lot of filamentation that's here that's not present here. This is just the Laplacian of that field. But you see you've got all this structure, and as time goes by, that tends to be dissipated by small-scale processes. So if you look at a simulation, and you have a good model, like what you were just talking about, then energy is going to be completely conserved in a two-dimensional turbulent simulation if your resolution is good enough, but enstrophy is not. So enstrophy, even if you have very fine resolution, enstrophy tends to drain out of the system. The only enstrophy that remains after you run a simulation like this is the enstrophy that's in the vortices themselves. So eventually you end up with a dipole where you have some vorticity in those vortex structures. That's why this doesn't go to zero. But everything else has been dissipated away by small-scale dissipation. Okay, so that was the idea that Bretherton and Haybogel did. Bretherton said, okay, now wait a minute. What we can do is, if you have a two-dimensional flow, what's going to happen is the flow is going to evolve to a state which has a minimum possible entropy, but has the same energy. So we can do this in a variational calculation. You do the total entropy, which is the relative vorticity. This is a barotropic flow, flat surface, so infinite deformation radius. You have the relative vorticity, and you also have the topography. So I'll show the equation looks like this. So here's your vorticity equation. You have d by dt of the relative vorticity and the Jacobian of stream function n zeta plus h. So the potential, what we call the potential entropy, is actually the sum involved. It's the square of the sum of the relative vorticity and h. That's right. It's a scale topography. Yeah. So it has units of 1/seconds. Yeah. But that's right. Exactly. So yeah, so that's a scaled version of the topography. And then, so what you're going to do now is we're going to minimize this function, and then we have a Lagrange multiplier here, and then we conserve energy. So we just do this variational calculation. If we calculate the first variation, you just do this, you take the variation of it, and you end up with this. This is the Euler-Lagrange equation. It looks like this. So del squared psi minus lambda psi equals minus h. That is, so if this is, if this is obeyed, then this works for any perturbation of the field. Okay, and this is equivalent to saying basically that this is the same condition that you get if you're looking for steady solutions. So if you have a steady solution to the vorticity equation here, so this is 0, then you have that zeta plus h has to be a function of the stream function. If you just say this is a linear function, so you have a linear, what we call Q-psi relationship, then you recover exactly the same thing. So minimum entropy is giving you a steady solution. So those two things are equivalent. Okay, you could solve this if you do what we were talking about in the coffee break. If you do just a Fourier transform, a 2D Fourier transform, so we'll say we have a periodic domain. We're going to expand this in Fourier modes, and then you can solve it trivially. You can get this solution. So the stream function, which is the pressure field, looks like the topography, okay, divided by this factor. And the factor, so this lambda is the Lagrange multiplier. But what you can see is that if k squared is much larger than lambda, so that's when you have small scale structures, this goes like h over k squared, which means that you're essentially going to 0. But as k squared is smaller than lambda, so that's large scale features, this is just h over lambda. And that's recovering the topography, okay? So what it means is that the solution is a low-pass filtered version of the topography. You know the topography, then you know what the stream function looks like, approximately. And this is their solution, 1976, doubly periodic domain. No, this is in a basin. Sorry, this is in a basin. And they started with a I think this is 64 squared. So we're talking about that, 64 squared grid points, something like that. Topography here, this is the initial stream function, this is random. And then after a period of time, this is the later stream function. If you compare this one to that one, what you see is that they're very similar, right? So you have, here are seamounts, and these are high pressure regions. These are basins over here, and you have low pressure things. And if you look carefully, you can see that a lot of the small scale structure has been filtered out. So really it's like a low pass filtered version of the solution. So you wait long enough, and all the entropy is dissipated away, and that's what you get. Okay. Now, to test whether it's a minimum entropy, we can take the second variation. And if you do the second variation, you get this. And if we do a Fourier transform, we end up with something like this. So this is positive definite as long as lambda is greater than minus the minimum wave number squared. Okay, and I'll show you a picture of this in a minute. But it's going to be positive that. And then we know we have minimum entropy. So basically, if lambda is positive, we have a minimum entropy solution. Okay. And interestingly, this is going to be important, I think, too, that Carnevale and Fredrickson, who took also a different approach to this, showed that you can prove stability of this flow in the Arnold sense under the same conditions. So you get exactly the same condition that you have here. And so if this parameter is positive, then that flow is also going to be stable. Okay, so here's what the solution looks like. This is an elliptical basin. And this is with a Lagrange multiplier, which is just equal to 1. And we have the relative vorticity looks like this. This is the total potential vorticity, and this is the stream function. And these two things are exactly the same because lambda is equal to 1. So this is equal to 1 times that, and that's why these are the same. And what you see is that the flow is similar to the topography. Sorry, the flow over here is similar to the topography, but you do have flow across the isobaths. So it's a smooth version of that. You know, the higher wave numbers are being filtered out, and we have something which looks more circular. Okay. Yep, sure. So lambda is determined by the energy constraint. Thank you. Perfect. I'll pay him afterwards. Yeah, that's fine. Yeah, that's right. So lambda is lambda is what determines the energy. So if we have our initial energy E naught, it's not simple to do this, right? You have to basically do this iteratively, but you vary lambda until you match the total energy. Okay, so this is the figure, this is what this looks like. Carnevale and Fredrickson sketched this diagram. So George Carnevale told me he did this by hand. So, and we calculated it later from a different solution in a basin, and we got the same thing, and George thought that was great because his sketch was correct. But it looks like this. So the energy, if you plot this as a function of lambda, is decreasing monotonically. So it goes like lambda squared, 1 over lambda squared as you go into large positive values. But for negative values over here, you get discontinuities, right? So if lambda is negative and it's equal to one of these k squared values, then you get these infinite values over here. Okay, we'll be talking about these later on too. But for the range of values, so the range of values that are known minimum entropy, it's from that first, it's on the right-hand side of that first discontinuity. So all of those values are minimum entropy. On this side, according to the second variation, you don't know if it's a minimum entropy or not. Okay. Now there's something else that's interesting out of this, and this was not in Bretherton and Hayvogel. And what I'm going to do, this is what happens when, let's say we have a solution over here and we decrease lambda. So we're going to decrease lambda towards 0, and that basically means we're going to increase the energy in the flow. And this is what happens. So if you look at the total PV, so that's this field here, and I'm going to now adjust lambda down towards 0. It does this. So here's lambda equals 10. So the PV is large and negative. In this case, it's dominated by the topography. But as lambda gets smaller, the PV becomes weaker and weaker. So eventually you get to a state where the PV is just flat. Okay, you have a flat surface. So the PV is becoming homogenized. All right. Now, why is that? Because what you're doing here is you're minimizing this function here. You're minimizing this function here. As lambda is going to 0, then you're trying to make this thing as small as possible, right? So zeta is basically going to cancel h. So those two things become equal and opposite in this limit. So you get PV homogenization from this. And this is also going to come up later, too. Okay. Yep. 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 He was. Yeah. Yeah. So David was studying this too, and I was at Scripps in February, and I was talking to Bill Young, and Bill's been working on this now too. So, and they also found the homogenization as well. So, yeah, but that's a good point. That if David talked about homogenization, I need to, because I should add a reference to that. Anyway, good point. Okay, here's a solution. This is a numerical solution. So now we're going to step forward this is this equation over here, the QG equation, the one-layer QG equation, which is this. We'll step this forward in time. This is my postdoc, Andre, who's doing this, and he's using a code which is in Julia. So it's over on this thing called geophysicalflows.jl. So this is it's a Julia code doing this. And this is an example. This is a circular basin, and here's a circular seamount. And this is the total potential vorticity early on, early stream function, and this is at a later time and a late stream function. Okay. What you can see is what I mentioned before in that picture from the Lofoten Basin, that there's an asymmetry in both of these things. Over the basin, the red, which is the cyclonic vorticity, is being strained out into filaments, whereas the anticyclones tend to be more circular. There's a merger asymmetry here. Up here, it's the exact opposite. So over the seamount, it's the anticyclones that are being strained out and the cyclones which are remaining. Okay. So, and what happens is after a long period of time, you get this. So you have the red, which is a cyclonic flow. That's predicted by the Bretherton-Hayvogel approach, and this is an anticyclonic flow over the seamount. But what's unusual is you get these vortices in the middle, okay, because these have opposite signs. So here I have a cyclonic flow, and then right smack in the middle, I have a very strong anticyclone. So there's an anticyclone. And same thing up here, I have an anticyclonic flow, but I have a cyclonic vortex right in the middle. Okay. This was noticed, the same thing was noticed in some simulations by Solidoc, McWilliams, and somebody else, Andrew. So, yeah, anyway, they were doing some simulations as well. This is using a primitive equation model. Not Andy Thompson, no, Andrew, the other Andrew, who's there at UCLA. Right, just blanked on his name. Yeah, okay, but you know. Anyway, this is a primitive equation simulation. Stuart, thank you, yes, right. And they, after a period of time, they get exactly the same thing. So here's a flow. This is now primitive equations, but same sort of thing. You can see the asymmetry in the vortex mergers happening over the basin. And then eventually you end up with a cyclonic vorticity from the large-scale field, and then you have that negative anticyclone in the middle. Okay. So that's exactly the same thing. So this paper was from a couple of years ago. All right. Now, if you integrate, so if you take the vorticity equation and you integrate it over a contour, then you get two terms. So you get the net circulation inside the contour, and that should be balanced by the net flux of vorticity across the contours, right? And that's what happens here. So the red curve, the blue curve here is the circulation, and the red curve is the net flux, the integrated flux of vorticity. And what you see is that there's an initial adjustment, but then after a period of time, after t equals 40 or so, you develop this cyclonic circulation. So that's this. And that's balanced by a net flux. So the net flux, what that means is that you have an influx of cyclones into the basin. Okay, so there's, on average, there are cyclones that are migrating into the basin. Now that's a little strange, because if you know the literature on the motion of isolated vortices, cyclones tend to move up a PV gradient, and anticyclones tend to go down a PV gradient, right? So what you would expect is that an anticyclone should be propagating into a basin, and cyclones should be expelled from the basin. That's true. That's true. Yes, that's true. Yeah. But even this, I mean, if you have a relative vorticity on a beta plane, for example, that's what will happen, right? That's exactly what happened. Because if you consider this as zeta plus h, then this is a negative thing, and this wants to go back up to its neutral latitude, right, where that's being balanced out. Okay. So this is different. And the reason why this happens is because essentially you have a sink of cyclonic vorticity. So when you're running simulations like this, the cyclonic vortices, when they come into the basin, they're essentially stripped apart and they become this cyclonic background stratification, whereas, circulation, whereas the anticyclones can then leave again. So anticyclones will come in and go out, but the cyclones don't leave again. They come in and then they're chewed up by this in this circulation. Yeah. Yes.
So what would the PV region are we seeing?
Yes. Yeah.
The red region there. White region.
That's right. Yeah. So the PV in this case, I know for a fact is, well, actually, this is it here. This is relative vorticity plus H.
All right.
Yeah.
Q.
This is Q. This is the full Q. They plotted relative vorticity, but this is the full Q. So it is negative. So it isn't homogenized. It's not homogenized. But I'll show you a case that is. So it's when you go to higher energies, you get homogenization. Okay, but before we do that, this is a case when you have an elliptical basin. All right, both of those cases before were circular basins. Here's an elliptical one. Same thing is happening. You have this asymmetry in the mergers over the basin and over the seamount. But at a late time, so you have a cyclonic flow, but you have a much, much smaller vortex. There's that storm. That's all right. Oh, it's raining now, too. Look at that. Okay, so the vortex is actually smaller. So in this case, if you don't have that circular basin, you get a much smaller vortex. Now, why? And the reason why is that a circular basin so it's symmetric in the radial coordinate, and it's actually a special case, because when you have circular bathymetry, you actually have momentum conservation. So what that means is that if you start with essentially zero momentum, you have to evolve, sorry, not in this one. Start with zero momentum, you have to evolve to a state where the momentum is still near zero. And so if you have cyclonic circulation here, you have to have anticyclonic circulation somewhere in the basin. But so anyway, so from now on, we'll just look at elliptical basins. We won't look at the circular case, because that's the special case. Okay, and here's the last thing on the one. So we have, no, it's not the last thing, but this is the Q-psi relationship from this elliptical solution here. And what you see is that it's close to linear. So it's close to linear. You do have these spikes at the end, and those are the vortices which are in the middle of the basin and the seamount. But otherwise, it's pretty linear. So that's consistent. All of these facts are consistent with the minimum entropy solution. So we're evolving to something like that. Okay, so here's the last question about the homogenization. That run, so these are circular runs, but here, if you have an energy of 0.05, this is the potential vorticity. It looks like this. So you have the Q, and you have this is the basin, and this is the seamount, I think. If you increase the energy by a factor of 10, then you get this homogenization. So the PV does get homogenized at the larger energies. And then in that case, these center of vortices are not trapped. Okay? It's like what you've done is you've erased the PV signature of the basins, and they just move around as if it's a flat bottom. So you see this kind of motion now happening. Right, they take a long time. Yeah. So it takes a long time. This Julia code is fast, so it runs pretty fast. But yeah, you're right. You have to wait a long time. Okay. All right. Now what I'm going to do, though, is because these are all barotropic calculations, and so now what I want to do is go to a stratified case, and the simplest one is a two-layer case. So we're going to take potential vorticity. We have potential vorticity in the upper layer, potential vorticity in the lower layer. These are the perturbation PVs. And now we have a total energy, which is a kinetic. We have the kinetic energy in the upper layer, kinetic energy in the lower layer, and then we have a potential energy term, and we have some parameters here. But we can take the same approach. So we can define we can define this quantity, which is like the scaled surface enstrophy, the scaled deep enstrophy, and then we conserve the total energy from there. Yes, thank you. Yeah, those should be gradients. Yeah, thank you. Yeah. These are actually gradient. That's great. There should be a gradient in there. Gradient psi1, gradient psi2 squared. Yeah, because it's u squared plus v squared. Okay, so we take the first variation and you get this, and if you integrate by parts, particularly the energy term, you can rewrite this as this. So you have this thing times dq1 and this thing times dq2. These two things should be zero independent of each other, regardless of these perturbations, dq1, dq2. So you get the Euler-Lagrange equations, which are just steady conditions, again, for the two-layer flow. So if this is, you have this, and you have the upper layer equation is steady, and if you have this, the lower layer equation is steady. So exact same thing. The minimum entropy calculation gives you steady solutions with this linear dependence. Okay. Here's what the solution looks like for lambda equals 1. So this is the relative vorticity, and this is the total, this is the potential vorticity. And what's that? 1 is the upper layer, sorry. 1's the upper layer and 2's the lower layer. Yeah, so this one is the lower layer, that plus h, yeah. And what you see is, so you look at the relative vorticity. So this is cyclonic flow, and you have cyclonic flow up here. This is bottom intensified. So it's stronger near the bottom than it is at the top. And same thing here. This is Q2 plus H. You see this is slightly weaker, not much. This basin, I didn't say this, but this basin is about 5 times the deformation radius at the surface. So this is, which is a reasonable size basin, not huge, but a reasonable size basin. And when you have that large a structure, then you end up with something which is close to barotropic. Okay, I didn't plot the stream function because it's exactly the same as these two over here, just based on these steady solutions here. Okay, the second variation looks like this, and this is a bit more complicated, so it's not quite so obvious how to work with this, but what you see is that if lambda is positive here, then this is positive definite. So we do have minimum entropy solutions for positive values of lambda. And the other thing is that you can extend that Carnevalian-Fredrickson argument. So this is the same condition for stability. So this is like saying that if lambda is positive, then these are going to be stable solutions. Okay. Again, as in the one layer case, you get PV homogenization. So as lambda is decreased towards 0, this is in the lower layer, then you have exactly the same thing. So the PV gets weaker and weaker and weaker, and then eventually it goes away. So as the flow becomes more energetic, it becomes homogenized. This one's the surface is a little different though, because when you have large lambda, so that's weak flows, you have no PV here either. So as this increases, you see this goes down. So this is a non-monotonic behavior. It gets up to here. This is 100, that's 10, and then that's 1 and 0.01. So the PV in the surface layer has this non-monotonic behavior. It's strongest at intermediate energies. Okay, so that's something that's going to come up here too. All right. So comments, flow is bottom intensified, and the solutions with positive lambda are minimum entropy, and they're steady. And they also can be used to prove that we have this. Okay, now here's the energy though for this. The energy looks a lot like what we got in the single layer case, right? So here's the positive lambda over here. It's decreasing over here as lambda increases, and we have these singularities on the left-hand side for these negative values, okay? So for most of the time, we focus on these positive values of lambda. So Bretherton and Avog only talked about the positive values of lambda. Okay, but there's something interesting here too. Over in these negative values, and again, the negative values, we don't even know if these are minimum entropy. They might be maximum entropy, so we have to be careful about this. But over in this range, so this, what is this? This is a measure of the surface intensification. So this is the maximum of the surface stream function divided by the maximum of the bottom stream function. What you see is that for lambda greater than 0, this is always less than 1. So these are bottom intensified solutions. But on this side, and it's true over here too, if you have large negative values, you have this. But there's a range of values in here where we have surface intensified solutions. So we actually have something surface. So we got kind of interested in this. It was why. So these, you can have something which is 20 times as strong at the surface as it is at the bottom. All right. But we don't know what they are. We don't know if they're minimum entropy. So what we did is we used a numerical routine to basically perturb the solutions and look locally around these solutions. And these solutions which have asterisks are local minima in enstrophy. So everything that has an asterisk here is actually a minimum, local minimum entropy. Okay, it's not a rigorous proof of it, but it's it apparently is happening. These are all minimum entropy, which is correct. But there are some of these values, including the peak here, are actually, so they're surface intensified and probably minimum entropy as well. Okay, and this is what one of those solutions looks like. This is lambda equals minus 26.5. What do you get? Well, you get, so you have a negative relative vorticity. That's an anticyclone. So we have an anticyclone, and you see it's much stronger at the surface than it is at the bottom. So it's definitely surface intensified. And the potential vorticity is also negative. So we have this negative PV, and we have very little expression down near the bottom. So we have something which is like, has almost no bottom expression, but has a surface intensified. Okay. But it's, again, this is a basin scale, because the basin is about the same scale as this. So this is a basin scale feature. All right. So singularities for negative lambda, some of these are surface intensified. Whether they're minimum entropy is not clear from the second variation, but it seems like some of them are. Because the second variation is sign indefinite, it may mean that these solutions are unstable. Okay, so you may be able to realize this thing, but it's not going to last. It's going to break up. Okay, so here are some simulations. Now two-layer simulations. This is the upper layer potential vorticity, and this is the total PV in the lower layer. And in this particular case, what Andre did is he initialized the flow where the PV was entirely in the lower layer. So there's no PV in the upper layer. And when you run it forward in time, you get a cyclonic flow in the basin, and you have an anticyclonic, small anticyclonic vortex in the middle. So it's almost exactly like the single layer case. And that makes sense because the flow is also bottom intensified, but has the same sign in both layers. So this initially bottom intensified flow gives you something which looks very much like the one layer case. That E value is, that's a good question. Actually, I don't know. Because you have to do the calculation for a double basin like this. You have to redo it. All my lambda values previously were single basin cases. So this is something different. I don't know offhand. Okay, but I'll show you what happens with higher energy. So we'll come back to that. All right, this is what happens if you start now instead with PV in the upper layer. So only PV in the upper layer. And what happens is you evolve to a state like this. You have very weak PV at depth. So you do have cyclonic flow. So there's your cyclonic flow and anticyclonic flow over the seamount. But you have these big vortices which are trapped up at the surface. Okay, so there's that big anticyclone that's trapped over the basin. Right. If you look at the PV budgets, this is for the lower layer. And what you see is that the cyclonic circulation is developing, just like in the one layer case. And that's balanced by an influx, so a negative flux of PV here. So these are cyclones coming in. But it's the opposite in the upper layer. So in the upper layer, the circulation is becoming negative. That's that single vortex here. And that's balanced by either an outflux of cyclones or an influx of anticyclones. So anticyclones, on average, are now coming in the upper layer. So we get two different behaviors depending on which layer you're in. Okay. Here are the Q-psi plots for those two cases. So this is the initially bottom trap case. And first off, in the upper layer, you have basically zero. It's not quite zero, so it's a little bit of noise here. So that's just numerical. But in principle, this is just zero. But here, you have, again, this almost linear relationship between Q and psi with some vortices on the end. So this, again, looks like the single layer case. But this is what happens when you start with the surface. Here's the bottom. The bottom, look, there's a difference in the axes here. So this is 2 and this is 20. But this is, you have a linear relationship in the lower layer. But here, we get a negative, we're getting a negative relationship at the surface. So this is true for the positive Q, which is over the seamount, and for the negative Q over the basin. So we do have a negative Q-psi relationship for these vortices. Yeah, so that's the thing. These vortices are never actually steady. They move around. Yeah, they definitely move around. So they're cycling around. And I'll show you some. It also depends on the total energy level as well. So it depends on the trapping varies with the total energy. But yeah, they're rarely stable. And that we know from the Lofoten as well. This thing doesn't sit still. It tends to migrate around the deepest part of the basin. Yeah. Okay. Here's what you were asking about. So here are 3 different cases. So energy 0.0125, 0.05, and 1. In the energy is equal to 1 case, everything is homogenized. So the PV is all homogenized. We have these vortices in the upper layer, but they are just moving around freely. It's like they're not reacting to any kind of PV. And this is a slice through the PV here. There's Q2 plus H. You can see it's flat. And Q1 is just across, this is right across this line here. It's basically 0, and it's got this noise. Here's the intermediate case. This is the one we've been looking at. And there you have a slightly earlier time. I've got 2 anticyclones and 1 cyclone. But these are trapped. So these will stay put. And you can see that Q2 plus H is negative. And so it's not homogenized in the lower layer. But this is one that was kind of interesting because this is the weak energy case. And what you have in this case is that, again, the upper layer PV is weak. It's almost near 0, but the vortices aren't trapped. Okay. So the deep PV is actually strong, very strong in this case, but the vortices don't seem to know about it. So one of the ideas that have been proposed for the reason why you have something like a Lofoten vortex is the vortex is interacting with the bottom and then self-propagating in across the topography like this. Well, this would be a perfect case for this because you don't have very strong deep flow, so the basin PV is almost unperturbed, but the vortices don't care. In fact, the vortices have no flow in the lower layer, so they can't interact with the bottom because they have 0 flow in the lower layer. So something else is going on with this vortex trapping, so it's no vortex trapping at large energy or at the weak, only at the intermediate energy. And the background PV over the basin, the seamount is near 0 in all 3 cases, not negative as predicted. So the other thing is that the minimum enstrophy solution would have, in this case, should have a negative PV in this whole basin, but it's not there. So apparently what happens is these vortices take that weak vorticity and just wrap it up. Yeah. Yeah. So, yeah. Okay, but you can get that if you run a different case. So it all depends on how turbulent the flow is. Here's a case where I start with anticyclonic flow trapped at the surface. So this is like that negative lambda solution, and it evolves into something. So this is not stable, it's unstable. You end up with a weak negative PV around here, and then most of it concentrated in that vortex. So this is what we think. We think what's happening here is that as you're minimizing enstrophy over the basin, you're evolving towards one of these negative lambda states. But because it's unstable, it doesn't stay like this. You evolve to a state where the vortex breaks up and then the vortices merge, and so you end up with something which is axisymmetric in the middle of the basin. So I do have some left over, which is associated with the bottom flow, but primarily the flow reorganizes into these compact vortices. This is the opposite case. This is what happens if you start with a cyclonic flow over the basin. What happens is that basically all of this breaks up into vortices, and all of those drift up there, and all the anticyclones break up, and all of them drift down here. So you end up at the same place, essentially, but from very different starting positions. Okay. I guess I got a couple minutes, but we ran this too with primitive equations. This is actually where this work started. I was working with a PhD student, and she was doing simulations using ROMs of the Lofoten Basin. So she was looking at this, and these, of course, permit things which are not allowed in quasi-geostrophy, like finite interfacial displacements and large-scale topography and larger Rossby numbers. Well, because it's not an isopycnal model, though, so it's a sigma coordinate model, right? Yeah. So it's continuously stratified. Yes. Yeah. So there's no layers here, just continuous stratification. Okay. But basically the same sort of thing happens, but there are a couple of differences. All right. So this is the surface vorticity in a case with no bottom friction, and you see you see this, what we saw in that low float and basin case too. There's a strong asymmetry in the surface between the cyclones and the anticyclones. This is actually less clear in quasi-geostrophy. So this is apparently due to having larger scale interfacial deflections. But when you let this go in time, you end up over here. So you have a bottom-intensified cyclonic flow, and then you have that anticyclonic circulation in the middle. This is what happens with bottom friction, and I think this is one important point here too, is that of the two flows, so there's two components of the flow, the deep flow and the surface flow. Of course, the deep flow is the one that's susceptible to bottom drag. So if you have bottom drag here, that's going to kill that cyclonic flow, but it leaves the vortex, the surface vortex, behind. And if you look at, interesting, if you look at the cross sections of the vortex, so this is the deformation radius in this case is about 20 kilometers. So that's about the scale of that vortex. So it's about a 20-kilometer radius vortex. Here is this cyclonic flow, and you see it shielded. So there is an outer shield of positive vorticity outside of that. But when you put in the bottom friction, it kills this off, and then what you see is this vortex actually does reach the bottom. So that's another difference with these primitive equation solutions. The vortex does actually reach all the way to the bottom. So it didn't do that in QG. No, there was no bottom friction in the QG. Consistent, yeah, exactly, yeah. In QG, yeah, we did do this, but I don't remember. I don't think that we got much bottom flow there either, I think. No, I don't think so, yeah. So I think it's really, it seems to be, and the Rossby numbers here are not small, so it's like 0.2 or something like that. What the Rossby number is here. Yeah, and this was also, the solutions of Solidoc et al. Were also primitive equation things, and they got this, so they did a 2-layer case as well, and they had a very strong bottom flow. I asked them, so I went to UCLA and I said, what did you use for bottom friction? But I didn't get a straight answer. So yeah, they didn't know. So Solidoc was, he was in Israel, so he wasn't there. So, and the rest of them, they said, oh, not sure what the bottom friction is. Yeah. Yeah, okay. Anyway, that's probably a good place to stop. This is low. This is the time-dependent field from the low float, and this is what the time average looks like. And you see that all these other features disappear. You have this cyclonic outer ring, so that's the deeper flow, and then you have that coming. Okay, so minimum entropy solutions in 2 layers are calculated. There's 2 components. One is bottom intensified if you have a positive lambda, cyclonic flow in the basin, and negative PV. So this is one that's well known. It's very much like the single layer Brotherton and Hay-Vogel solution. But this one is the one which is interesting. It's surface intensified with anticyclonic surface PV, and it may be an entropy minimum. It's not, and again, it's a little bit of we're out on a limb here, because we don't have a definitive statement that that's what that vortex is. Because again, the trapping is mysterious. Why the trapping occurs in intermediate energies and not at the weak energies and strong energies. So there's still some puzzling aspects about this. But the one thing that's consistent across this is that you have this asymmetry in the vortex mergers. So, and that's true in all layers, single, double layers. You definitely see this, and that favors axisymmetric anticyclones over a basin. So it really seems to be that this is an aspect of turbulent flow. Yeah, so QG simulations, we have no flow at the bottom, and we have a negative Q-psi relationship, which means it might be a negative lambda state. So this is from a friend of mine who's a marine geologist. I don't know why I don't care about the bottom of the ocean, but I don't. So, yeah.